Next presentation will be made by the Racurs representative, Alexey Smirnov, who has been working on UAVs for quite some time. He has been studying the UAV technology and all other things related to them. Mr. Smirnov, you have the floor. Thank you very much. In fact, now we heard possible problems related to legislation related to UAV use, and I can say that there is no single document on how to use UAVs in Russia. Still, at the moment, there are considerations to introduce something in the law, but it is still at the level of first readings. And the simple manufacturer or production survey company who bought a UAV, at the moment, for them to sign any contracts, they need some kind of document which would confirm that their system can do this or that work with certain type of quality. For that, a voluntary certification system was organized for UAV systems, and one of the organizations which was assigned to do the certification was the Moscow State University of Survey and Cartography. And as long as I am also partially involved in this, one of the chief issues discussed there on the development of the technology for certification itself was the calibration of cameras which are mounted on UAVs. Why? Because UAVs are quite small. They have a small weight capacity, as it was mentioned earlier. Big professional aerial cameras simply are not mountable on small UAVs. But small, regular consumer cameras, none of the camera, unfortunately, is not originally designed for aerial photography. And now, what I wanted to tell you in my report, I will tell you a bit how certification is organized in MIGAIC, how cameras are calibrated, again based on MIGAIC experience, what research is being done during the calibration, and what results can be acquired and analyzed when using different methods of calibration for consumer cameras. The calibration of cameras is done in two stages. First, laboratory calibration and field calibration. At the same time, laboratory calibration implies stationary conditions, but stationary conditions for the use of consumer cameras are not efficient, because when using a consumer camera in the air with the random photography by the UAV, in fact, all the camera parameters are distorted because of external factors. That's why field calibration would be the best process. And in the past few years, some projects on aerial photography were done on geo-testing ground of the Minsk State University of Survey and Cartography. It is a densely marked area with control points, and we did calibration for different types of UAVs and different classes of cameras. Different types of cameras which in principle can be used on UAVs. There are only three types that I've selected. First is a non-professional single lens cameras. Second is a professional consumer camera with the replaceable lens, with bigger size of matrix and the required number of adjustments for different weather conditions. And third type is something in between consumer cameras and professional aerial cameras. In this case, you can see medium format cameras. This is phase one of Hasselblad cameras. The actual area of the testing ground for calibration is the lot of about 4 square kilometers, and when calibrating the acquired results, we can use different methods. First method is laboratory or field calibration as a rule. They're done using standard methods, and standard methods include the so-called physical distortion. This is Ronald Conrad formula. But after multiple experiences, we found out that because of the external factors, because of using, as it was mentioned earlier, the shutter mechanism, and because of some other problems related to consumer cameras, sometimes the classical calibration provided not acceptable, but not the best possible results. As a result, virtually all photogrammetric systems that was used to process the data from these UAVs would show a process of self-calibration. And when switching on this self-calibration, as far as the photo mod is concerned, for instance, there are two types of calculation of distortion. First type is the classical physical distortion method, and the second option is the mixed distortion. In this case, mixed distortion is a distortion with an addition of about a couple of dozens of coefficients, which help us calculate additional corrections, or which increase the quality and precision of the acquired result acquired from this type of data. Consequently, the main task for us was to understand what kind of calibration type would be acceptable for this or that type of UAV or for the different types of cameras, because that was the main factor which affected the final result, because any certification is based on the analysis of the final result, whether it was in line with the required standards. And the first test, we used phase 1 camera, because this camera is of much higher level than any consumer camera, and we believe that its results will prove to be a reference result. We did 2 flights, 2 acquisitions for 2 different areas and 2 different sizes of pixels, 600 meters and 800 meters. And the number of control and checkpoints here, you can see 109 points, and control points, and 19 checkpoints. And you can see that they are all over the area here. Specification of the camera, and specification of the UAV that we mounted the camera on. We can say that the most importantly, it has the central shutter, which already. So basically, it's not a slit shutter, and it doesn't distort the frame. And very good size of the matrix, 50 megapixels. And this size of the CCD at certain altitude will get us a very good basis and very good angle. And this, the model of UAV that we mounted this camera on was the medium class Orlan 10. Its specifications can be viewed on the screen. It is one of the largest UAV models in Russia, which can be launched and landed freely. And the parameters of camera calibration that we came up with after the post-processing. Here you can see the calibration parameters without calibration. So these are the parameters which were in the instruction, and I can tell you that the phase 1 camera is not calibratable. Those people who think that phase 1 camera is aerial camera, there are many different facts which confirm the lack of certain parameters in this camera compared to all known cameras like UltraCam, DMC, AGI, and others. In fact, we can discuss them at masterclass tomorrow. Next, you can see the results of laboratory calibration and all sorts of self-calibrations. There are two types of self-calibrations, which can be done not from scratch, when we mount the camera without calibration, and we do some calibration in the software. And there are also options when we could use laboratory calibration as the first pre-calibration, when we could see whether the parameters would be more accurate when using self-calibration and laboratory calibration as an initial pre-calibration. Here you can note that I selected first of all the focal point, and you can see that the focal length wise the deviation is not that much, because the camera is of quite a high class, despite the fact that in phase one we used consumer lens. Still, the class of the camera is quite high, and it allowed us to be variable about its calibration for any class. In fact, it is quite a high result, good result. And now speaking about the main point. Here we have an interesting thing, because there are different calibration software use different main points. What do I mean here? There is a auto calibration point, and there is the so-called zero distortion point. So I must tell you here that during laboratory calibration, we selected zero distortion point. As a result, it led to a shift in y-axis 1.1 millimeter, which is a lot. Whereas in regular calibration, field calibration, the main point is located somewhere in the center. In fact, it just means that this PPA and PPS in this particular case are located not in the same point. And the distortion coefficients, as you can see, they are not really different from each other. And the main analysis was done for the results, but I will show it to you at the end of my presentation.
Next test is from non-professional camera Nikon. This image taken from 700 meters, pixel size 5 centimeters. Camera specs, UAV specs. Was done using Ptero G0. As for the camera, it uses a plane shutter, so we get image distortion, frame distortions during angular evolutions. But this camera is the best in terms of imaging quality, even better than Phase 1. I could corroborate that with examples. Here you can see calibration parameters to see how they differ from Phase 1. Calibrating such camera is vital, as we can see. Secondly, distortion coefficients also differ from physical and from mixed one. We will see results at the end. Test number 3, involving Sony NX5. These are small, non-professional cameras with 16mm focus, 250mm altitude, and GSD 7 centimeters. This time we used a Micro class UAV. It also uses a plane shutter, and the matrix size is smaller. So the results of calibration are similar to Nikon, where there are a lot of divergences in focal length and in distortion. As for further uses, we needed to check the efficiency by checking polar distortion. At Racurs, we have developed software that allows calculating distortion field at any point of the image. I'll try to show it very quickly. This is a viewer. All you need to do is open a text file with known parameter calibrations. Well, let's look at radial distortion. So this is how you can view it, and the window duplicates the full frame size. You can see how the numbers change. Here I provided a slide on lab calibration. This is the pixel number with the greatest distortion. Then there is physical self-calibration. It uses the same formula. Now let's use mixed self-calibration. The difference is 2 times. There is a 2 times difference. The field of distortion before mixed self-calibration dramatically changes at a certain time. So the question is, how can you obtain the result with all of that? Self-calibration itself is shown in 3D models by various utilities. This is XY of an image, and Z shows the difference between X and Y. So what do we have with phase 1? The plane area, the smallest one, appears when you use the mixed self-calibration. It can be used without laboratory or with laboratory calibration. And according to Z-axis, it includes both laboratory and physical self-calibration. And the difference is actually only several centimeters. One could say millimeters. Why? Because it's the type of camera, this type of camera. If we look at different projects done at various altitudes, the higher the flight is, the basis is bigger and the angle of intersection is better. Now let's look at non-professional cameras. It's much more interesting. When using regular calibrations, the height area when using lab calibration plus self-calibration, mixed self-calibration. This was for Nikon. The same applies to point-and-shoot cameras and Sony. What conclusions can be made? For a plane area, you don't have to make an error. In fact, it's a misconception. It appears that if we have performed our project incorrectly with bad geometry, it means that self-calibration will also be bad, and you can see the difference in quality. we have mirror at the testing ground that can calculate resolution. Also, you don't have 100 points per 4,000 kilometers in production. So calibration results will be totally different. It means that for plane mistakes, planers, we can try to use software self-calibration, but lab calibration is always needed as first approximation. That's all I have. Thank you very much. Your questions? What about accuracy? What was the final accuracy for Nikon and Sony? It's small print. I couldn't make that out. For Nikon, it was 10 centimeters in plane, and in height, it's 12 centimeters only in one case. I mean, in GSD. 2 GSD in plane and 3 GSD in height. Thank you very much, Alexey.